we're going to continue talking about mixing from a more parametric point of view. So in essence, what we've seen before is that mixing can be caused by shear production or buoyancy production. And mixing can be destroyed by what process, we said? What is the mechanism that balances this shear production and buoyancy production? Dissipation, remember that dissipation. And that's what the early measurements on turbulence, that's what they focused on, measuring dissipation. But anyway, what we're going to see how we can parameterize this in a bulk manner today. And we see that the mixing can come from stresses. And those stresses can be derived from wind, from bottom, or from internal stresses in the middle of the water column. And then we see that instabilities produce mixing also, but not necessarily related to stresses, but related to buoyancy input like cooling. Cooling will cause convection of the water column. Double diffusion also can cause convection both in the vertical, both upwards and downwards. And we saw that tidal straining can cause also mixing. How does tidal straining cause mixing? Because tidal straining, we said that can cause stratification, right? So tidal straining can cause both stratification and mixing. Remember what tidal straining is? No? Do you remember? No idea? Tidal straining is the interaction of the vertically sheared tidal flow with the horizontal density gradient in such a way that during ebb, the ebb phases of the tide, the current strains the density field to stratify it, and during flood, the flood currents strain the density field to cause instabilities at the surface and cause rapid mixing. So that's tidal straining. In essence, from the concepts that we've talked about, tidal straining means stratified conditions during ebb and destratified conditions during flood, or increased stratification during ebb and decreased stratification during flood. That's what tidal straining is. So in this case, tidal straining can cause mixing also. All right, so we're going to see that mixing. We've said this, that mixing comes from wind stress, bottom stress, tidal straining, and cooling. So we have to find a way in which we can quantify how much energy per unit area or how much power goes into the water column for each one of these four agents that cause mixing. And mixing will cause a water column to destratify, but what will cause it to stratify? What mechanisms we talked about will cause it to stratify? What mechanisms will compete with these mechanisms to avoid mixing of the water column? Any that come to mind? How about the opposite of cooling? Heating. Heating will cause stratification, right? How about will tidal straining cause stratification? Yes, we just discussed that it will. What else will cause stratification? Maybe the estuarine circulation. So estuarine circulation, tidal straining, and heating are the three mechanisms that we're going to see how we can parameterize. So what we're going to do today is we're going to try to find a quantitative expression on how much energy per unit area, or how much power rather, that is energy per unit time per unit area, how much power per unit area or per unit volume goes into the water column from each one of these 7 processes. Well, cooling and heating are the same. Tidal straining is the same. So it's really from wind stress, bottom stress, tidal straining, cooling, and estuarine circulation. How can those produce stratification or mixing? Any other mechanisms that may produce stratification or mixing that we haven't considered here that you can think? What other mechanisms add buoyancy to the water column, for example? What happens, think of the higher latitudes, what happens when the ice melts? When ice melts in Antarctica or in the Arctic, that adds buoyancy. Right? So melting is something that we're not considering there. How about here in Florida, when we are in the think of the Ponce de Leon Inlet. What happens with a heavy rain, heavy downpour? That adds, directly from the rain, it could add stratification. So we'll see how much rain we need to have in order for us to be able to see the effects on stratification. So in order to do that, to be able to represent these mechanisms quantitatively, we need to understand what happens in the water column. So here you have, right here you have a stratified water column. The center of mass is given by that point. And then in a mixed water column, the center of mass is right in the middle of the water column. So in order to mix a water column, we have to bring the center of mass from here to here. Do we agree that the center of mass of a stratified water column is right there? Why is it right there? Why is it below the mid depth line? Because the denser water is concentrated toward the bottom, so the center of mass is below the mid water level, right? And we also agree that for a mixed water column, the center of mass of that water column is right in the middle of the water column. Do we agree on that? If we agree on that, then the rest of the arguments will be reasonable. So again, in order to mix a water column, we have to raise the center of mass from a depth Z2 to a depth Z1. So we have to do work to raise it, right? And that work is the mixing that we have to apply to the water column. That work will represent as that letter phi. So what mixing does, essentially, it increases the potential energy of the water column. That's what mixing does. And how much are we adding to the potential energy? That's exactly what we need to find out. What is the value of this phi? Okay, so in general, if we go to high school physics, you probably remember that the potential energy is given by mass times gravity times the height of an object, right? So it's the energy that an object occupies just by virtue of the position where it is. So that is the potential energy of the water column. But we can also say that the potential energy per unit volume, if we divide this potential energy over the volume, we get mass over volume, we get density. So this is the potential energy per unit volume in the water column, rho times G times H. But in reality, or in most cases, that density depends on depth, if we have a stratified water column. If it's a mixed water column, then the density doesn't depend on depth, right? So we can say then that the potential energy per unit volume is going to be given by gravity times the integral of the density over the entire water column. That's going to be the potential energy of a stratified water column. Potential energy per unit volume. And the potential energy per unit area of a mixed water column is given by this expression. This is for a stratified water column. That's the potential energy now per unit area, because we're integrating it throughout the entire water column. So up here is per unit volume, but since we're integrating here, that makes it per unit area. So that's for a stratified water column. And for a mixed water column, we have that the potential energy per unit area is given by this expression. Notice that the rho hat is the average density in the water column. So the rho hat is that's what the average density in the water column is. The integral of the density throughout the water column divided by the density, that's the average density. So in essence, what we want to find out is the difference between these two potential energies. How much energy do we need to convert this one to that one? That's what we need to do. So what are the units of this? Potential energy per unit area. So you see gravity has meters per second squared. Density is kilograms per cubic meter. And then we have meters squared here. So that gives us kilograms per second squared. And if you work out the unit, you can see that that's energy per unit area. Energy is, remember the units of energy? Joules, or kilograms times meters squared, second squared. So that's energy per unit area. Kilograms times meter squared over meter squared times second squared. So that's how we end up with kilograms per second squared. All right, so keep in mind that, that those are the units. So what I was saying before is that we need to find out the difference between the two, the mixed water column and the stratified water column. We're trying to find out the energy that we need to bring the center of mass from the stratified water column to the mixed water column. That's how much energy we need to input in the water column to mix it. So the difference is given by this expression, gravity times the difference in densities between the mixed water column and the depth-dependent density integrated over the entire water column. So we're going to call that phi. So that's the difference. So we're going to call this the potential energy anomaly. So that's a difference between the mixed and the stratified water column. And it has units of joules per square meter. Energy per unit area, joules per square meter. So again, it's the energy required to mix the water column completely, the energy required to bring the profile from a depth-dependent to a uniform profile. So it's called, again, the potential energy anomaly. That phi is called the potential energy anomaly. So there it is again. This phi is a proxy for stratification. The greater the value of phi, the greater the stratification is. What happens if phi equals 0? If phi equals 0, it indicates what? That is mixed, that we don't need to add any more energy to mix the water column, it's already mixed. So phi equals 0 means that there's no stratification. And the greater the phi, the more stratified the water column. There it is, that's what I just said. So that's the potential energy anomaly. So what we're really interested in when we look at the water column from the energetic point of view, when we try to compare mixing versus stratification, is to determine whether the water column remains stratified or whether it mixes as a result of the forcings acting on the water column. The forcings that will try to stratify versus the forcings that will try to mix it. Right? So this is a competition, like any sports or any competition that you can think of. See who's stronger, the mixing people, the mixing agents or the stratifying agent. So in order to determine who wins the competition, we need to study these changes of the potential energy anomaly in time. So energy per unit time is what? Is power. So that's why we have the units of d phi dt is watts per square meter. So what we're trying to define here, what we're trying to represent in this competition between mixing and stratification is we're trying to find a quantitative expression for this. The changes of potential energy in time as given by mixing effects from wind, mixing effects from tides, stratifying from heating or versus destratifying from cooling, stratifying from tidal straining versus destratifying from tidal straining, and stratification from the estuarine circulation. We'll discuss in a minute why we talk about stratification from estuarine circulation and not necessarily why would be more correct to talk about stratification instead of from estuarine circulation. Stratification from what? That's right, the river input. That's what I heard. The river discharge, right? So the river discharge, we don't know how the river discharge is related to the estuarine circulation nor to the stratification. We just conceptually think that when we add river discharge to an estuary, it'll stratify. It might stratify, it might not. We've discussed that, and we'll come back to that discussion in a minute when we try to represent the stratification from estuarine circulation. Okay. So first, we need to find how to represent this mixing from wind. How would you start doing this? Well, you probably printed out the notes so you know where we're going from. But okay, see. So first we're going to discuss how to represent the mixing power from the wind. Okay. And that power per unit area generated by the wind at a height of 10 meters is given by, represented in a different, slightly different language. This is the same thing as what says above here. So this is given by the wind stress multiplied times the wind speed at a height of 10 meters. So that's how much power per unit area is being generated by the wind at 10 meters. The wind stress times the wind speed. What are the units of that? The wind stress has units of what was that? Yeah, I think you said it right. But pascals, but it's kilograms. Maybe. I have to do it. But pascals, right? Force per unit area or pressure. And that if you multiply times times a velocity, you'll get power per unit area. You can do it also. Okay. And we can represent the wind stress, remember, as density of the air times this C sub D. That is, what is it? I don't remember. It's not the canonical.
I forgot.
It's physically it's the same thing, but it's at the air-water interface, right? Not at the water-bottom interface.
0.00116.
So it's the same order of magnitude, 10 to the minus 3, but it's around 1.
0.00116.
Around 1 times 10 to the minus 3, right? How about the density of the air?
1.2 into 10 power something. Kilogram per meter cube.
1.2 to the what power?
This is 1.2 kilogram per meter cube.
That's right. Does that make sense, that 1 cubic meter of air weighs 1 kilogram? It sort of makes sense, right? It's hard to imagine that because it's 1 cubic meter of air. So about this much air weighs 1 kilogram. And the wind speed at 10 meters squared, that's a wind stress, but we're multiplying it times the wind speed. So that's how we can represent the power per unit area. But that's the power per unit area at 10 meters height. We need to find out how much power the wind generates at the air-water interface. What do we need to use then? Instead of this W at 10 meters, we need to use the stress velocity at the surface. So we need to use that W star. And the W star, if you remember, is the stress divided by the density, the square root of that. So again, the stress is given by density of the air, drag coefficient, wind speed squared divided by density. And then we have a wind speed squared, the square root of that gets it out of the square, the root. So then we have that the W star, the stress velocity at the air-water interface, is just a fraction of the wind speed at 10 meters. And that fraction is given by this ratio, the square root of this ratio. And that square root equals approximately what? Do you remember? Remember, density of air is order 1. This is 1 times 10 to the minus 3. So we have 1 times 10 to the minus 3 divided by density of the water, which is order 10 to the third. So we have the square root of 10 to the minus 6, which is 10 to the minus 3. Right? So 0.001. That's approximately what this square root tells us. So stress velocity at the air-water interface is around 0.001 of the wind speed at 10 meters height. And the power generated by the wind at the air-water interface is given by this expression. Just a small fraction, 0.001, of the power generated at a height of 10 meters above the seawater, above the air-water interface. Remember that fraction is 0.00116. I think that's what you said before, right? Taking into account those values. Right? All right, so that's one expression. There it is. That's one expression for the mixing power from the wind. So we can start building. If we go back to here, we can start building this equation because we now know how to represent this mixing from wind. And that mixing from wind is given by that expression. Notice that we have a minus sign there. Why do we have a minus sign? You think? What is this representing? What is this quantity representing?
It's going to get smaller because of wind.
Exactly. Wind will tend to destratify the water column. So this will tend to decrease with the wind stress. Now, what's the problem with that argument that I'm saying? The problem with that argument is that we're assuming that the wind will only mix the water column. It will not move. It will not cause currents that might stratify also the water column. So there's a problem with this representation. So you can think of a way of representing both the mixing power from the wind, but also the stratifying power from wind. So if you can come up with a parameterization, that would be a good contribution that you'll make to the field. All right, and where does this value come from? This 1.3 times 10 to the minus 6. We go back to the expression. So that's by multiplying this one times the air density of the air times the drag coefficient. And that gives us, well, this 1.3 is only the drag coefficient times the fraction, that fraction 0.00116. Okay, but there's also another representation from that other people have come up with, that the power generated by the wind per unit area is given by this expression, which is analogous to that, to the one up. Here, this delta is a mixing efficiency coefficient that people have used as 0.023, this delta. And this kappa sub s is a drag factor that equals 6.4 times 10 to the minus 5, which equals also the drag coefficient that we used before, and the ratio of the current versus the wind. Do you have any idea what this ratio is? The speed of the current versus the speed of the wind? Any idea from what you've seen in lakes or in the ocean? When the wind is blowing 10 meters per second, that probably doesn't mean anything to you, right? 10 meters per second is around 20 knots. Or when it's blowing at 5 meters per second, which is approximately 10 knots, how strong of a current would you expect? Say when it's blowing 5 meters per second or 10 knots. How strong of a current would you expect?
1 knot.
1 knot? So 10% of the wind. That's what you're thinking. So say 1 knot. You weren't at St. Andrew experiment, right? But that's way too high. The bottom line is that that's way too high. A 10 knot wind producing a 1 knot current, that's way too high.
0.5 knots.
0.5 knots.
1 knots.
Yeah, it's around 1% of the wind speed. So this U over W is somewhere between 1 and 4%. 4% would be the largest, this ratio. Okay, so this of 6.4 times 10 to the minus 5 comes from that ratio. And if you use this value, 6.4 times 10 to the minus 5 for K sub S and 0.023 for delta, then you end up with a coefficient of 1.4 times 10 to the minus 6, which is very similar to the expression above. So you can use whichever you feel more attracted to for when you represent the effects of wind forcing on mixing the water column. Okay, so now, given that we've known or we've seen how to represent the mixing power from winds, how would you represent the mixing power from tidal currents? Would you do it the same way? Would you use the analogous? For the wind, we use the wind stress, right, at the surface. So for the tidal currents, we use analogously the bottom stress from the tidal current. So it would be the mixing power from the tidal currents would be the bottom stress times what? Times a velocity, right? A velocity near the bottom. So the power per unit area generated by tidal flow interacting with the bottom is density times, what's this? All right, that's the bottom drag coefficient. The canonical value is 2.5 times 10 to the minus 3. At least you've learned something. And then times the velocity at the bottom cubed, averaged over the tidal cycle. Right? So on average, this would be the power per unit area produced by the tidal flow interacting with the bottom. But only a factor of these goes into mixing, just like only a factor of the wind speed at 10 meters goes into mixing the water column. Only a fraction of these goes to mixing. Only a fraction of these goes to mixing, and that's given by this mixing efficiency. So notice that this expression is analogous to the same multiplied times the mixing efficiency. That's using the instantaneous value of the current. If we use the amplitude of the tidal flow, which is given by this u sub naught, then we need to use that 4 over 3 pi, which you obtain from a Taylor's expansion of the velocity as a function of sines and cosines. So that's where that 4 over 3 pi comes. But notice that it's the power per unit area generated by the current. Only a portion of that, given by the mixing efficiencies, goes into mixing. And there are several values of that mixing efficiency reported in literature, the range going from 2 times 10 to the minus 3 to almost 4 times 10 to the minus 3. And you've said the only thing you've learned in this class is the bottom drag coefficient. Is it true? I hope not. Not even that. Well, if you haven't, there you go. All right, so we haven't another expression yet. Again, whether you want to work with the instantaneous tidal current or with the amplitude of the tidal flow, you use either of those two expressions to add to the equation that we're building, right? To try to determine the changes in stratification. Changes of stratification with time. That's what we're trying to do here. Up to now, we've only seen the mixing effects from wind and from tidal current. So now we're going to see the effects of tidal straining. And tidal straining can mix or stratify with water column. Let me backtrack. See if you're awake. Does tidal straining mix or destratify the water column? Or destratify the water column? Yeah. Well, she's paying attention because she's saying it's the same.
That's why I was confused.
You were questioning it. You weren't sure.
I was just making sure I heard you.
It's the same thing, right? Mixing and destratification is the same thing.
Neither.
Okay, so how about does tidal straining increase stratification or increase mixing? It does both, right? So we need to find an expression that does both. How do we do that? So that's more tricky. Well, to do that, we're going to have to go through some background here. We see that we can determine the potential energy anomaly given by that expression. So the trick here is to try to find a representation for the density, the structure of the density profile. And we can do that. Okay, so let me backtrack because I got ahead of myself. So we have the potential energy anomaly right there, the changes in potential energy anomaly in time, or the changes in stratification, can be given by this expression. Right? So now we're differentiating this density with respect to time. So we need to find now an expression that can represent these changes of density with time. Any ideas on how we can do that? What would you use? Would you use something that looks like that? Maybe. What are we doing here? What is this expression? Remember, we're trying to represent these changes of density with time with an expression. So the first one we choose is this one. What does that represent? Does that tell you anything if you just look at this part? What does that tell you? Nothing? Blank eye? Well, first of all, the left-hand side of the equation, what does that tell you? d rho dt. What does that represent physically? There's no trick there in that question. No trick. It's a simple, stupid question.
Change the density of time.
Thank you. And now the right-hand side of the equation, what does that represent? U, what does U represents a flow, right? And d rho dx
Changes from
a density gradient. Right? So it's just the advection of a density gradient. The advection of a density gradient. So if we consider that this change of mass only by the advection of mass in the U direction, in the x direction. Notice, what are we missing here from this expression? We're missing the advection in the v direction, v d rho dy, and we're missing w d rho dc. If you want to be picky, we're also missing the dispersive part of this. That is the mixing, the diffusive part. The terms that include the divergence of the flux of density. Right? So, but just to simplify things, we're representing d rho dt by this expression. So it's advection in one dimension, right? And similarly, for the vertically average density profile, we can represent it like that, by the advection of a vertically average current of a vertically average density gradient. Notice that the U hat is a vertically average current as represented here. So what do we do with these expressions? We seem to understand them now. What do we do with them? We put them right here, right? Instead of putting d rho dt here, we put minus u d rho dx here. And instead of putting, there. Instead of writing d rho hat dt here, we write minus u hat d rho hat dx. That's what we do. And also assuming that the along-extreme density gradient is independent of depth. So we can plug these two in here, and the d rho dx comes out of the integral because it's independent of depth. So now we see that the changes of stratification produced by an advection of a density gradient can be given by this expression, gravity times a horizontal density gradient, multiplied times the integral of the difference between the vertically sheared profile in flow minus a vertically average flow. So this doesn't depend on depth, right, because it's vertically averaged. Okay, so we have that expression. Now can we use it yet? Or what do you think we need to do to find the value of this, d phi dt? To find the value of this, what do we need from that expression? We know that G is 9.8. We can give a density gradient for any particular situation. How about this? Do we know the profile of U with respect to depth? Yes? How would you represent it? Would you have a general expression for U as a function of depth? So that's what we need to do, right? In order to be able to determine d phi dt, we need to get an expression for U. And there are many options that you can choose from, I think. One that comes to mind immediately is that, I think you said that, right? The law of the wall, you said? Is that what I heard?
Yes.
Okay. Remember, my hearing is not good, so I need to make sure. The law of the wall, you can use the law of the wall to represent this, but we're going to use a different one, just for the sake of using another one. But we can also use the law of the wall, as I'll show in a minute. So we can use a representation of U as a function of depth. Here, this zeta is a non-dimensional depth. It's Z depth divided by the total water column depth. So it's a non-dimensional depth. So notice that it's a parabolic profile because it depends on depth squared. So that profile looks something like that. At the surface, where Z equals 0, this term equals 0. So the flow at the surface is U hat times 1.15. If U hat equals 1, then the flow at the surface is 1.15, let's say, meters per second. That's if we assume that the vertically average flow is 1 meter per second. And then at Z equals minus H, zeta equals what? At Z equals minus H, zeta equals minus 1. So minus 1 squared, 1 times 4.425. So 1.15 minus 0.425 equals 0.72. So there you have the parabolic profile with 1.15 at the surface and 0.72 at the bottom. So you can use that analytical expression for the flow and put it in plug it back in the expression that we had just represented. But you can also use the law of the wall. Here I show some data that we got in 2007. I think, yeah, last year, almost to the date. It's the black profile, so that's the tidal current you see here in centimeters per second. And if you use this Bowden and Fairbairn profile, that's given by the blue line. That's a Bowden and Fairbairn. And then if you use the law of the wall, which is represented right here with these two parameters, U star of 0.04 meters per second and a length scale of 4 millimeters, then you get that red line. So somebody took this idea already and ran away for their project, for the term project in this. They're going to use, she's going to use the law of the wall to compare it to the Ponce de Leon data particular, and see what kind of variability one gets for U star and for the length scale. But as you can see, the point here is that you can choose any representation. The point is that you grab this and plug it into the representation for the changes of stratification given by tidal straining. So the first step is to subtract the U from the vertically averaged U, which is U minus U hat. And that gives you here, U is 1.15 minus 425 zeta squared, and U is this one. So U minus U hat gives you this expression. So this is the one that's going to go into the integral, into this integral here, U minus U hat. So there's U minus U hat, there it is again. It's 0.15 minus 0.425 zeta squared. So you put this in here into this integral, you evaluate the integral, and if you evaluate the integral, this is a relatively straightforward integral, right? It has integral of zeta and integral of zeta cubed. So, and you evaluate it from minus 1 to 0, you get that value, 0.031. And just to make sure that you remember how to do these things, you can do it at home. There's the answer, 0.031. So the bottom line here is that for tidal straining, you can represent the changes of stratification as 0.031 times G times H squared times the horizontal density gradient times the vertically averaged U. So that's a representation. So how would you represent from this equation, or from this equation, how would you represent when it stratifies and when it destratifies? Depending on the sign that U hat should have, right? Depending on the direction of the vertically averaged flow, if it's going in one direction or in the other. So when this is positive, d phi dt from tidal straining will be positive, which means stratification or destratification? Stratification. So U positive will be what? Ebb or flood. During ebb, will the water column stratify or destratify? During ebb, it'll stratify. So U positive will mean, for this particular representation, U positive will mean ebb, and U negative will be flood. So that's the third expression, right? How many have we collected so far? 3. For wind stress, for bottom stress, and for tidal straining. The first two destratify the water column. Tidal straining can destratify or can stratify the water column. Okay. So there you go. You read that, so you knew. Okay, so the next stratifying agent that we'll consider is from estuarine circulation. And we use the same concept again. We assume that the estuarine circulation will strain the density field, will also strain the density field. So think that when the outflow is stronger, it'll advect more fresh water toward the ocean, but at the same time, it'll bring more salty water in. So that an enhanced estuarine circulation will produce an enhanced stratification. That's the assumption. So the trick now is, again, as we did for tidal straining, is to represent this difference inside the integral. So before we use a profile that could be the law of the wall or the Perlman-Fairbairn profile that I showed to represent this U. But now for estuarine circulation, what profile would you use? Do you remember? We derived an analytical representation for that U. And you worked with it in a homework. Right? Outflow at the surface and inflow at depth. Remember what it looked like? Well, you have it written there, of course. There it is. Does that look familiar? Notice that I've non-dimensionalized the depth also. This is z over h. That's zeta. And also notice that u minus u hat equals only u because u hat is going to be equal 0. There's no net flow for S-train, for this representation for S-train circulation. Remember this representation? You work with it in the home. Do you need another homework to remember? No, right? You don't need. Okay, good. Because if you want another one, I can come up with it. All right, so what do we do with this now? Any idea? What did I say we need to do with this thing? You know, right? But just embarrassed by how silly my questions are. You integrate. You use this, put it in here. We know that u hat is 0. We integrate from minus h to 0. In this case, from minus 1 to 0. Integrate these from minus 1 to 0. And we find that the integral of this expression from minus 1 to 0 is 3 over 20. There's another exercise there for your integration. So 3 over 20 multiplied times this coefficient. Notice that from this integration we get this extra h squared. So the bottom line is that for the S-train circulation, the changes in stratification are given by 1 over 3 over 20 multiplied times this. Notice how sensitive this representation is to the depth of the water column. So it means that the deeper the water column, the more this assumed mechanism will stratify the water column. And it makes sense, right? That the deeper the water column, it's easier to find stratified conditions in the water column. But so it's very sensitive to the depth of the water column, and it's also sensitive to the longitudinal density gradient, d rho dx, because it's d rho dx squared. Right. Any questions up to here? So this is our fourth representation. Right? Wind stress, bottom stress, tau straining, S-train circulation. All right. The next one we'll consider is from heating and cooling, and that directly comes from this expression. The changes in stratification are given by this expression where Q is the heating rate in watts per square meter. So notice, what are the units of this, we said? On the left-hand side of the equation, we have the units are. It has to be the same as every other expression that we've derived. The units are, so remember we say power per unit area, watts per square meter, watts per square meter. And notice that this Q, the heating rate or cooling rate, is also given in watts per square meter, which means that alpha times G times H divided by 2Cp, their units must cancel out. In this alpha, does anybody know what alpha is? The thermal expansion coefficient, right? G is gravity, H is depth, and this is the specific heat of seawater. The thermal expansion coefficient depends on temperature and salinity. People tend to use typically that value 1.6 times 10 to the minus 4. But notice where that falls. 1.6 is falls in this range of salinities and temperature. So for the salinity of the ocean, that it's around 35. Can you see that? For the salinity of the ocean, which is around here 35, there an arrow there? Did I lose my arrow? No. The salinity of the ocean is around here, so that corresponds to a temperature of around 10 or 11 degrees, corresponding to this thermal expansion coefficient. So you can see the range of values that the thermal expansion coefficient can attain as a function of temperature and salinity. What that means is that does everybody know what it means, that value of 1.6 times 10 to the minus 4? Or let's say to use this value of 2 times 10 to the minus 4 per degree Celsius. What does that mean? What does it mean that we have a thermal expansion coefficient of 2 times 10 to the minus 4? It means that for every degree Celsius change in temperature, you'll have a 2 times 10 to the minus 4 change in density. So what that means is that it's a 0.2 units in the sigma t sense, 0.2 change in density, 0.2 change, 0.2 kilograms per cubic meter change for every degree Celsius change of temperature. That's what it means, and that's for that range, for those ranges of salinity and temperature. Okay, so if I notice that at high temperatures, that thermal expansion coefficient is larger. It's around 3 times 10 to the minus 4. So what that means is that at a temperature of, when the water temperature is 30 degrees, typical of the summer here in the lakes and in the coastal waters, every degree change of temperature will cause a change in density equivalent to 0.3 kilograms per cubic meter. That's what it means. Got it? All right, so that's the thermal expansion coefficient. Then C sub P is the specific heat of water, and that equals 4,000 joules per cubic meter, 4,000 joules per kilogram per degree Celsius. Does everybody know whether that's a constant or what does it represent? What that represents is that we need to apply an energy of 4,000 joules per kilogram of water to raise its temperature by 1 degree. Or we have to extract 4,000 joules per cubic kilogram. I keep saying cubic. 4,000 joules per kilogram. You have to extract an energy equivalent to 4,000 joules per kilogram to decrease the temperature of seawater by 1 degree Celsius. So, do you have any idea whether this is a constant value or how much it varies? It doesn't change as much as the thermal expansion coefficient, so it oscillates near 4,000 joules per kilogram for all ranges of temperature and salinity in the ocean. And Q here is the cooling heating rate in watts per square meter. Okay, so there's the next expression. And yet we have another one before we take a break. We can have an expression for changes of stratification produced by rain. And that's given by this expression. G is gravity, H is depth. Delta rho is the density difference between the fresh water and the ocean water. Pi is the precipitation rate divided by 2. How would you normally report precipitation rates? Inches? Inches rate? Yeah, that would be the amount of rain, right? Inches per unit time, right? So, but millimeters per day or would be more, well, maybe you're more used to inches per day, right? So it's a rate, meters per second or millimeters per hour, millimeters per day, inches per hour, inches per day. But for this expression, you should use meters per second. So you have to convert your precipitation rate to meters per second. Okay, so before we take a break, let's take a break. Let's take a break so that we can come back to this interesting discussion.
It's not recording right now, right? It's not recording.
No recording.
All right. Might be. Let's try this.
I don't know if it's. I don't know if it will do it unless we say stop recording or continue recording.
All right. Stop.
What do you want to say?
Stop.
No.
Nope.
No, because then it generate another file. Or maybe it's okay.
All right. No.
What do you want to do?
Maybe you can use something shorter. What is that? Show the arrow. Then maybe it will not. The arrow will not
Disappear?
Yeah, I think so. And he asked me to do something in. I explained what happens when you use the
animation?
Yeah, animation. And he asked me to change the this one. Wait a second. All right.
Yeah, we'll do it.
Right.
I'm not using animations today, so
Okay.
that's okay. Don't worry.
So Dr. also used his computer?
Right. But he's not teaching today. It's food, right?
I really don't know want to relate to that, probably.
actually great.
Oh, yeah, that's rough.
Yeah.
Yeah.
There So how was your break? Go do anything?
Yeah, try to catch up. I got further behind. It's typical, pretty typical. We're missing Mike. He is. So we've seen how to represent the increase of stratification from tidal straining and from estuarine circulation. But the main buoyancy of fresh water for an estuary comes from river discharge. So the trick is how to represent this river discharge. And I mentioned this before. I think that this is a big open question, that we don't know how an estuary responds to river discharge. We don't know effectively. We have some relationships on how it responds to river discharge, and we'll discuss a little bit more of this maybe in 2 or 3 more lectures. But we don't know yet exactly, because sometimes with an increased river discharge, depending on the dimensions of the estuary, you can have enhanced stratification and enhanced estuarine circulation. But also at the same time, depending on the size of the estuary, you could have just the fresh water washing all the salt, or not all the salt, but a lot of salt out of the estuary, and decreasing stratification, that is having really more fresh water in the vertical profile and less of an estuarine circulation. So depending on other aspects that I think I haven't mentioned, but this is something that requires a very thorough and detailed study. And again, if you can come up with a relationship between stratification as a function of river discharge, then you have it made. That's going to be a huge, huge contribution, huge impact, because we don't have that yet. It depends on too many things. Well, I don't know on how many things, but you can come up with a relatively straightforward way. And this is something that it's already been discussed here. There's no simple way of dealing with freshwater input, because the discharge is not distributed uniformly over a prescribed area, as is the case of wind stress, bottom stress, rain and heat. So the alternative way of representing the riverine influence on stratification is by assuming that increased river discharge will enhance the horizontal density gradient. As mentioned, that might not be the case all the time, because increased river discharge may not mean increased density gradient. So if we assume that each of these mechanisms that tend to stratify and destratify the water column can be summed independently, so then the change of stratification of the water column will be a summation of all of them. We can represent them we can represent the stratification in the water column by that expression. Okay, so let's look at a few examples to see how we can use these relationships in sort of real situations. So let's compare the stratifying tendencies of rain, which typically we don't consider, as compared to a low heating rate of 10 watts per square meter. So that's probably that rate of 10 watts per square meter doesn't mean much to you. Do you have any concept, say on a sunny day, what the heating rate from the sun is, from shortwave radiation. Do you have any idea on a sunny day?
130 watts per meter squared.
How many?
130 watts per meter squared.
100?
132.
Exactly? Yeah, one is around 200. So between 100 and 200 watts per square meter. So that's just to give you an idea that we're right here considering a small heating rate. We're going to compare it to the stratifying tendencies from rain. So using all these expressions that we've collected, we can say how much rain do we need to be equivalent to a heating rate of 10 watts per square meter. So a heating rate of 10 watts per square meter, so if we put 10 watts per square meter there, using alpha equals 1.6 times 10 to the minus 4, the heat capacity of seawater 4 times 10 to the third, and a depth, a water column of 10 meters, then the power, the stratifying power from that heating rate equals 2 times 10 to the minus 5, well, equals 1.96 times 10 to the minus 5, or approximately equal to 2 times 10 to the minus 5 watts per square meter. So now how would you determine how much rain do you need to equate to that stratifying power? Right, so you use the expression for the stratifying power from rain, which is this one, remember? Delta rho is the density difference between rainwater and ocean water. This is what this piece of art we said? The precipitation rate. So this is what we're looking for. We know that the stratifying power is 2 times 10 to the minus 5. So using h of 10, g is also order 10. And delta rho, what is delta rho? What delta rho would you use? What value?
Between the rainwater and...
Yeah, what value would you use?
20.
Very good. Well, 20 is a nominal value. You can use somewhere in the vicinity of 20. So you can see that you can solve for the precipitation rate, and then you'll get 2 times 10 to the minus 8 meters per second. So probably that doesn't mean anything to you. That means 1.7 millimeters per day. That perhaps still doesn't mean much to some of you. 1.7 millimeters per day is like a little more than half an inch per day. So that's a precipitation rate that is not unusual, right? So that can stratify the water column in a similar way as a heating rate of 10 watts per square meter. So as you see, precipitation rate in some cases may enhance stratification, direct precipitation rate, not indirect through helping the discharge of the rivers, but just direct precipitation on the water. So that's something that we have completely ignored, and probably we need to think about sometime when there's a lot of rain. Where can this happen? Have 1.7 millimeters per day. Have you experienced that? In Vancouver, but every day. Well, here, yeah. So half an inch per day is not a lot of rain. It's rain, steady rain all day, but it's not a lot of rain. So we get those here often enough too. Right. So now let's look at another example. Remember, these are competition between different agents. Competition between stratifying agent heating. The stratifying agent that we will consider now is heating, and the destratifying agent that we will consider is bottom stress. So if we take the full expression, which of those are we looking at now? The stratifying agent from heating, which one was it? We called heating this one, I think. and the destratifying from bottom stress, which is this one. Yeah. So this is the destratifying power, or the mixing power from bottom stress, and this is the stratifying power from heating. Right, so we're looking at this balance. So if there's no change in stratification, so in other words, if buoyancy equals mixing, then d phi dt equals 0, and then these two equal each other. Right? And you can play around with some parameters to find out that the parameter h over u cubed, where u is the amplitude of the tidal current, is going to be equal to that. So for a prescribed heating rate, the only variables are the depth of the water column and the tidal current amplitude, because all these other, alpha is a constant, g is a constant. What's this? It comes from here, and it is the. That's right, and it equals
1.64.
You always give me 0.64 or 0.6. Where'd you get those? No. 4,000.
Oh, that was alpha value. I got confused.
Okay, 4,000. It's joules per kilogram per degree Celsius. And this epsilon we said is what? Is this epsilon that appears here? And it's a mixing efficiency, right? Not all of this amount goes into mixing from the bottom stress, just part of it. That's characterized by this mixing efficiency. That is also of order 10 to the minus 3, the mixing efficiency. Bottom drag coefficient, density of water. So again, the beauty of this parameter, h over u cubed, is that for any given prescribed heating rate, you can divide regions of stratified from destratified conditions using this parameter h over u cubed. Well, let's see how that works. So if Q increases here, then this one needs to increase to keep h over u cubed constant. So if Q increases, it will tend to stratify the water column. So in order to keep the same conditions in which buoyancy equals mixing, then the current needs to increase. If it doesn't increase, then the water column will stratify. So that's what it says there. So then this parameter h over u cubed is indicative of regions where mixed waters are separated from stratified waters. So that's called the Simpson-Hunter parameter. And this was a very fashionable parameter in the 70s, 80s, and even into the early 90s, that people were trying to define regions of mixed water columns from stratified water columns by looking at this h over u cubed parameter. Now remember, where will this work? In what areas of the world will this work, or should this work, this h over u cubed? What are the assumptions that we use to arrive at this parameter? The assumptions that we used was that the change of, that there was a balance between heating and bottom stress. No other sources of buoyancy, but from heating, and no other sources of mixing other than bottom stress. Right? So where you have estuarine circulation well developed, this might not work because you're not considering the stratification from that. You're only considering stratification from heating. Okay, so I'll come back to that. I'll show you several examples where this h over u cubed parameter has been used successfully. So all the coefficients are 1.6 times 10 to the 4. So going back, all these coefficients, when you get all these coefficients, multiply and divide, you get 1.6 times 10 to the 4th. So h over u cubed is 1.6 times 10 to the 4th divided by the heating rate. So here in this picture, we have the Seto Inland Sea in Japan. So this is the main island of Japan. This is Shikoku Island, Kyushu Island. The main island of Japan is called Honshu. So all this here is the inland sea. And you have the logarithm of the parameter h over u cubed. How can you construct this? Just by knowing the depth of the water column and the tidal current amplitude. That u is the tidal current amplitude. So by knowing those two simple parameters, you can construct this diagram, this contour plot. And the areas that are stippled, is this stippled? How do you call this shading effect? Is it stippled? Sure? Okay, let's call it stippled. So the stippled areas are where h over u cubed is small. If h over u cubed is small, it means what, you think?
Higher U.
Exactly, higher u, which means in terms of the energetics of the system, in terms of the potential energy anomaly, where h over u cubed is small, it means that if you have large u, you have a lot of mixing. So these are the mixed areas. The stippled areas here are the mixed areas.
Yeah, like where it's constricted.
Good observation. Did you hear that? That it tends to happen where it's constricted. Why is that?
Higher U.
That's where the currents are stronger. And at some point I'll show you some pictures. We have data of currents around here. And you can see the boils of the currents because they're very strong, so they generate a lot of horizontal eddies, horizontal turbulence. So in the constrictions, the tidal currents are very strong, a lot of mixing that produce these mixed regions. So where the tidal currents are weaker, then you have stratified conditions. So in this area it works very nicely because the buoyancy input from river is small, and a lot of stratification is caused by heating, and also because the tidal currents are very strong here, dominate the stratification processes. Here's another example. Does it say where it is? Oh yeah, it does say where it is. So what is this body of water called? It is an estuary. Long Island Sound. The interesting aspect of Long Island Sound is the main source of fresh water is the Connecticut River, and it's at the mouth of the estuary. So that's a weird estuary because it has a source of fresh water at the mouth. So anyway, here you have in the upper panel you have the stratification, or what's called bulk stratification, the difference between the surface and bottom density. And these red areas are areas of high stratification. And these blue contours circumscribe areas of low stratification, as observed from CTD casts. So you go do CTD cast and look at the surface density minus bottom density, and there's a high difference in this entire area, high difference between surface and bottom in this entire area, high difference. Low difference here and here. And that's those are areas. Well, here the strongest tidal currents in the sound are located here, and also there's a shoaling here that causes a lot of mixing. So these are the h over u cube stratification parameter, and you can see here these are low values of the h over u cube parameter. These are high values and high values. So it approximately emulates the regions where observed stratification is found. Another example. You can tell where it is. not geographically, but in the caption.
The
The Gulf of Maine. Where's the Gulf of Maine? It's a straight coastline called, no, it's not straight coastline, quadriculed coastline, Gulf of Maine, because these are results from a numerical model. So this is Cape Cod, and this is this peninsula is Nova Scotia. What happened with our Canadian?
It's like 3,000 miles away from her.
It's completely the other way.
Like it's talking about California.
Right, so it's sort of distorted this. So we're not looking true north here, but this is the Gulf of Maine. And this is called Nantucket Shoals, and this is one of these. What's this bank? Have you heard of George's Bank? George's Bank and Nantucket Shoals. And there are these other shoals off of the Cape. So these are areas of low H/U³ parameter. And notice that they can change. Well, so these are, let me see a second. Oh. These are the areas where when the tidal currents are strongest, these are the areas where the H/U³ parameter is smallest. So all these areas are mixed when the tidal currents are strongest. But this can change, obviously, from spring tides to neap tides. And that's what they did in this study, again, this numerical study. And you can see that the yellow region, so this yellow area, that is almost the same as the red, it's only the semi-diurnal current. So including in the simulations only a semi-diurnal current gives you very small H/U³ parameters at those areas. And the red line represents all the semi-diurnal in phase. So the strongest spring tide, so the perigean spring tides, as they are called. M2 plus N2 plus S2. That's the largest extent of mixed waters. That's when the strongest tidal currents of the month occur. Also, when the weakest tidal currents of the month occur, M2 minus N2, minus S2, which is the blue one. So those are the apogean neap tides. M2 minus N2 minus S2. So that's the smallest area of mixed waters, right? And then somewhere in between is where you have some neap tides that are not as weak, which is the red, green area. So the point here is that the extent of the mixed area can change according to the tidal forcing. So this H/U³ parameter obviously will change because U cubed, which represents the amplitude of the tidal current, cubed, will change from spring to neap tide. And it depends on whether you're talking about apogean or perigean spring tides, the extent will be different. Right? So, and it works well here. This, compared to observations, it works well here. In this area, the Gulf of Maine is mostly forced by buoyancy from heating, and is destratified by tidal currents. But it can also be destratified by white other mechanisms. In the Gulf of Maine, you can have strong winds. Right? So winds can also destratify. So this doesn't take into account the effects of wind. Now let's look at another area where we have the H/U³ parameters there. And this red line is circumscribing low H/U³ parameter, so areas where it's supposed to be low mixing. But before we continue, tell me where are we talking about? There's the latitude right there. See the latitude here? This thing is not responding. The latitude, 35 south. So where are we? What part of the world?
Argentina.
Very good. So this is Argentina. This is Argentina. This whole thing is Argentina. This estuary is, I've given an example of this estuary. Remember the name of it? the Rio de la Plata or River Plate. For those of you soccer fans should know. So that's the Rio de la Plata. So just north of Argentina, here's Uruguay right here. But anyway, the thing is that this is a huge estuary with a huge amount of fresh water input. And the H over U cube parameter predicts that it's going to be mixed, all these areas mixed, according to the H over U cube parameter. However, we know that this is a salt wedge estuary. So by no means is a mixed area. It's strongly stratified. But why is it that that the H over U cube parameter doesn't work there? Because the main source of buoyancy is from the river discharge, not from source of buoyancy from heating, not from heating. So keep that in mind when you see these diagrams of H over U cubed. You have to be suspicious whether the area where you're seeing these diagrams applies to the balance between buoyancy from heating and destratification from tidal stresses. That's the assumption for this H over U cube. So those are the restrictions of the approach, that the dominant stratifying power comes from heating and the destratifying power from bottom stresses.
So how can you define the high or the small number? 2.3 every time?
Yeah, usually it's depending on the heating rate. But it's going to be an area where you have large gradients. But yeah, here they define it as 2.3, right there. But it's the log, remember it's the log. The log base 10. And that's also, but that's a good question because it's tricky. People who have published on it have found the appropriate value, the value that suits the distributions best. But it works. I mean, it allows you to tell at what heating rate you have the differentiation between mixed and stratified waters. All right, so here's another example. And now with the estuaries driven by density gradient. So a system with a horizontal density gradient of 10 kilograms per cubic meter in 50 kilometers. Is that a reasonable value, would you say? 10, a horizontal density gradient of 10 in 50 kilometers. Yeah? What do you use in, Andrew, have you started doing any models yet? No? Let's see. Working on estuaries. What, John Woo, what value do you use? What horizontal density value do you use for your models? You don't know? You have a 35 salinity difference in like 100 kilometers, no? Something like that. So going back to the question, 10 density units in 50 kilometers, is that reasonable or is that large or small? Let's see, in Ponce de Leon Inlet, most of us were there. And probably you don't know the values because you haven't seen the data. But in, let's say, 500 meters, we have a density difference of 1, maybe. 500 meters. So can you extrapolate that? In 1 kilometer, maybe 2 units of difference in 1 kilometer. In 50 kilometers, that's what it is. I didn't know it was, but it almost works to the Ponce de Leon Inlet. 10 kilograms over 50 kilometers. And by no means that's a strong density gradient. So that gives us a delta rho dx of 10 times 10 to minus 4. If we assume that the depth of the water column is 10 meters, and the vertical eddy viscosity is 5 times 10 to the minus 3, is that a large value or a small value?
Reasonable value.
And that's tidally averaged, huh?
Reasonable value. It's a reasonable value.
Reasonable. Reasonable for what situation?
It looks like it's 5 times the normal value that you use.
5 times?
Usually it's 0.001 or something.
Yeah, so this is actually a little bit high. Yeah, so 5 times the value that I would tend to use. So this might be a little high here. Okay. So from the estuarine circulation, the mixing power, no, the stratifying power from the estuarine circulation, we know the value of G. H is 10 meters. A sub Z is 5 times 10 to minus 3. Rho is 1020. We can use 1025. D rho dx is 2 times 10 to minus 4 squared. So that gives us a stratifying power of 2.4 times 10 to minus 4 watts per square meter. So in order to balance that, how strong of a wind power do we need? We need the same wind power, which is how strong of a wind speed. So if we solve this equation for W10, we find that the wind speed required to overcome that stratifying power is 5.2 meters per second. Does that mean anything to you? Yes? What do you like to think of, in knots or in miles per hour? Hurricane? Well, knots is pretty common. So this is, in knots is around 10 knots. So that's not a strong wind that will overcome that stratifying power. And then, how strong of a current do we need? So from the bottom stress mixing power, if the bottom stress mixing power equals 2.4 times 10 to the minus 4, which is the stratifying power from that density gradient, then how strong of a current is it? Does that mean anything? That is a knot. So 0.5 meter per second. Again, we don't need very strong forcing to overcome that horizontal density gradient over 10 meters of water to keep stratification conditions the same. Now let's assume a system in which we have 1 kilogram in 3 kilometers. So in 50 kilometers would be... So there's more stratification than the previous case, right? And also deeper, 20 meters. And also less mixing, 10 to the minus 3. So now what we have is 0.1 watts per square meter, the power to stratify the water column. So this is 10 to the minus 1 watts per square meter versus, what was the other? The previous example was 10 to the minus 4, right? This is 10 to the minus 1. So 3 orders of magnitude difference. And again, that's because of the sensitivity of this relationship to the depth and to the density gradient. So we've increased the density gradient a little bit, and we've increased the depth also. We've doubled the depth. So that's why we have increased the stratifying power by 3 orders of magnitude. So now we need, what do you think? What kind of currents or winds do we need to destratify this? Any idea? If we're stratifying the water column 3 orders of magnitude more strongly. So we need very strong, yeah. As you'll see, you'll need a hurricane. So in order to balance the stratifying power, we need the wind power that's given by this expression of 0.105, which is this value, but now expressed in more significant figures. So we need a wind speed of 40 meters per second. Does that mean anything? Yeah, that's a hurricane wind. That's 80 knots. Well, close to 80 knots. Yeah, so. Yeah. That's a strong, very strong wind. Very strong. That's hurricane. And what kind of current? So you need a current of almost 4 meters per second. So that's rarely seen anywhere, right? So just in the narrow passages in the upper latitudes, where you have high tidal range and narrow passages. So you can see that the water column most likely will remain stratified under these circumstances. Okay, so you can play games with these parameters and generate figures like this one. This figure is the same as this one, and this figure is the same as this one, just represented in a different way. And what we have here is the change in stratification. The contours represent changes of stratification as a function of wind, different wind speeds in meters per second, and different heating rates in watts per square meter. So you have that negative heating rate means a cooling, and positive heating rate. So all this yellow area represent the parameter space under which you will have this stratification of the water column. So with negative heating rate, it doesn't matter whether there's wind or not, you're going to have this stratification. And you're going to have more destratification if you increase the wind. But in this part of the parameter space, that is all this heating, and regardless of the wind speed up to, let's say, for a heating rate of 500 watts per square meter, it doesn't matter that there's wind, it'll remain stratified. You have to get winds of 8 meters per second for the water to start becoming destratified. So that's what this represents. The same for this, but instead of as a function of wind, we have as a function of the current, tidal current. So we have between 0 and 1 meter per second. For all this parameter space, you have this stratification, and in this very small parameter space, you get stratification. Now, this diagram will depend on the depth of the water column and on the horizontal density gradient, right? So you'll get different distributions of these parameters for different density gradients and for different water column depths. So for these, I think I used the values of the first example, of the 2 examples ago, a depth of 10 meters and the horizontal density gradient of 10 in 50 kilometers. So with that, you get that you don't need much forcing to have these stratified conditions, as you can see here. So these 2 representations, like I said, are equivalent to this. So anything that's underneath the plane, the 0 plane, will represent this stratification, and everything above the 0 plane will represent stratification. So again, for any heating, you will increase stratification, and for weak winds, you will still increase stratification because you have heating. Same situation for here. All right, does that make sense, or do you want me to go over that again? Now this is for instead of heating, now we have the horizontal density gradient. And notice that we have a much bigger area of stratified conditions now. When you have a density gradient of 10 in 10 kilometers, that is 1 in 1 kilometer, it doesn't matter how strong the wind is, up to 10 meters per second, the water will remain stratified. Same for the current. It doesn't matter that the current goes up to 1 meter per second, the water column will remain stratified if you have a density gradient of 1 in 1 kilometer. So you can play these games to see where your favorite system will fall and what kind of forcing you need to expect mixed water column or stratified water column by playing games like this with this, investigating the parameter space for the possible horizontal density gradients that you can expect, possible flow, bottom stress forcings, and wind stress forcings.
How accurate is that, knowing that you only use bottom stress?
You can add to the dimension here by adding another one, and it's restricted to the assumptions that you use. Right? So you need to know what your limitations the limitations of playing these games is that you're ignoring, for example, for these two cases, we're ignoring heating as a source of buoyancy to the system. We're ignoring tidal straining also as a source of buoyancy and destratification too. So if there's a place where you can do that, then this will apply. Otherwise, you could add a third dimension, the effects of tidal straining, or so it can get complicated quickly if because you could add a fourth dimension or a fifth dimension if you want to include everything. So you're going to have some spheres that intersect with the hyperspace. And all right, so to conclude it today, we have this a couple of papers where they have used this approach successfully. Recently, there's been a few more, but in these studies, Simpson was the one who proposed the concept of tidal straining. In this paper, he talked about tidal straining and used it to calculate the energetics of the tidal straining. He was able to predict the stratification in Liverpool Bay successfully just from tidal straining, the competition of tidal straining and bottom stresses. So in that case, those two processes successfully predicted the stratification of the water column. And then here in small estuary in the Baltic Sea, they were able to look at the annual trends of stratification from, I don't remember exactly what stratifying agents they used in destratifying, but again, those are two examples that you can consult where they successfully have used this approach. All right, so before we adjourn, let me first I'm going to